morning. We're very pleased to welcome Damien Debecker from the University Catholique de Louvain in Louvain from the engineering faculty. I like to call it the engineering faculty. I know we don't, but it's now officially Faculty of Bioscience Engineering. This is like the department which now houses the chemistry and the chemical engineering departments is called the Department of Condensed Material and Nanosciences. Condensed material, of course, being what happens outside of the gas, everywhere except outside of the gas phase. The combustion chemists unfortunately retired before we opened it, so they didn't get thrown out. Damien did his master's and his doctoral degree in Leuven, then with Eric Guignot, and then did a postdoc at the Sorbonne and at the University of Manchester. And he's currently full professor, Faculty of Bioscience Engineering, and a holder of a Franke Research Professorial Chair. So without any more ado, I'm going to ask him to talk to us about carbon dioxide and hydrogen, catalyzing the road to sustainable e-fuels. So, thank you very much. The floor is yours.
I put my clock here to be sure that...
Yes, don't worry, I've got a loud bell on.
So good evening to everyone. Thank you very much for the invitation. It's my pleasure to be there tonight. And I hope the title will be quite inspiring. I have to tell you, I will talk a little bit about this, but not too much about the implementation of e-fuels, mostly about the catalytic reactions that we have to carry out between CO2 and hydrogen to get to that point. Right? So first, I always like to, with my students, I will also insist on that each time I'm talking about this. When we talk about CO2, we have the impression we have to save the planet. Okay, we have to do something about the planet. And I always tell them that it's probably a little bit more selfish than that, because what we are trying to protect is more our lifestyle. Okay, because if we don't manage to save the planet, or if we don't manage to solve the problem of CO2, maybe we will not have all the goods that we currently can enjoy, or the housing, or the food, the good food and wine, or the mobility, but the planet will probably survive even without us. Right? That's always a perspective that I like to mention. But this being said, we clearly have a problem with CO2. I will not spend too much time on this. Of course, we all know. So there is a problem with CO2, we know, and you all know that curve, which I'm not going to explain in detail, but basically it says that for millennia, the atmospheric carbon dioxide concentration was lower than this level, and now we are here experiencing that tremendous peak in CO2 level in the atmosphere. So we have a problem there, and it's of course because of us, because of the industrial revolution and the fact that we burn fossil fuels. So again, I'm not going to insist on that too much, just to say that it's being measured, it's being measured every day, continuously, and we are still on that rising curve very clearly. There's no other way to state it. We are still dumping a lot of CO2 in the atmosphere, and that's a problem. Okay. Just another quick reminder about the carbon cycle. So what we have to realize is that the problem we have with CO2, it comes from the fact that we base our development on a broken cycle. So we start from fossil resources that we take here, that we process in chemical plants, and then that we burn. Okay, and when we burn them, we emit CO2, of course. Now, you might say, okay, these fossil fuels, they used to be plants also, or biomass also. Yes, that's true, but that was million years ago. Okay, of course. So the process to get there takes millions or hundreds of millions of years, and this is going very fast. So of course, this is a broken cycle. Ideally, if we could have the same kind of industrial activity and consumption and emission of CO2 that would be synchronized, I would say, with the ability of biomass to be replenished, that would be a closed cycle and there would be no big problem. Okay, so that's just to set the scene. We have a problem with CO2, and I just mentioned a tree. So I will start there. A tree is a wonderful object because it's actually a photobiocatalyst, right? It's a photobiocatalytic system that is capturing CO2 and converting it into sugars, essentially, right? It works on solar energy, so it's clean. It's not polluting, of course. Instead, it's releasing oxygen, so that's not too bad. It's also good for biodiversity, for landscape, leisure, those nice forests. It's against erosion, etc., etc. So only positive things. Of course, we need to plant trees. We need to leave enough time to the biosphere to replenish and absorb at least part of the CO2 that we have emitted or that we are emitting. I left 3 dots there, so I will come back to this in a second. Despite the fact that we have the trees that capture the CO2, we are emitting too much CO2. So there are several things that we should do and that we are currently doing and that we hear all the time on the TV and on the radio that we should do. First thing is to avoid emission, so avoid burning so much fossil fuels. So of course the heating, the car, the fuels to have the mobility with the cars and the planes, etc., etc. One of the things we should do, we must do, is to decrease the burning of fossil fuels, of course. But probably that will not be enough, or at least it's already too late in a sense, it's already too late. So we will have to do more. And so one of the things that we can do is to do the capture of the CO2 at point sources. When I say point sources, it's the chimney of big processes like the cement industry, incinerators, big power plants, etc., which emit streams of gases that is CO2 rich. And then there's another option that I will briefly mention today, which is direct air capture. Okay, so we are now living in an era where we have 420 ppm of CO2 in the atmosphere. It's still very low, but it's too high. But 420 ppm of CO2 is something we can work with and try to capture that CO2. So in my view, we have to do all those 3 things, right? But I'm going to discuss, of course, not going to discuss this. This is a given. We have to do it. I'm going to discuss a little bit the bottom of this. So I was just telling you, we can capture CO2 at point sources. How does that go? How does that work? This is a relatively old scheme. It's in French also, I'm sorry. Showing how CO2 absorption works, okay? CO2 absorption with a B here, so CO2 is going to enter a phase, a liquid phase here. And what is this phase? It's actually a solvent, an aminated solvent. One of the examples can be monomethylamine. And in fact, the CO2 containing gas here is going in a column. And on top of that column, you have the amine, clean amine coming in. And then you have plateaus of exchange. It's like a distillation column. It looks like a distillation column. It's an absorption column. And the CO2 has a strong, which is an acidic gas, has a strong affinity for that basic molecule. And so it's going to be absorbed in the solvent. And you get a rich amine, a rich solvent here at the bottom. So you capture the CO2, but of course, you will want this amine to be recycled. Okay, you're not going to consume that amine all the time, so you need to regenerate it. So it's sent to another column where you will inject energy to provoke the reverse reaction to release the CO2. Okay, so you inject energy in the form of vapor here, and you release the CO2. There is H2S also here, but let's focus on CO2. So you have a concentrated CO2 stream, and you can decide what you do with it. But at the same time, you regenerate your amine, your clean amine that can be recycled. Okay, so that's just to say that it is possible to capture CO2 at point sources. That's something we can do, but there are some remarks. First, the solvent needs to be synthesized. There's an amine group here, so you need ammonia. Ammonia is one of the most energy-consuming processes that we have for the moment in the industry. You need a lot of energy to synthesize ammonia. It's synthesized by the hydrogenation of nitrogen. Okay. So a lot of energy there. As I told you, you have to regenerate this solvent, and you need energy here also to regenerate the solvent. So it's not free, right? If you say energy, you say CO2. Okay, so part of your CO2 is impacted by this energy there. And then also those amines, they are not innocent. They have some toxicity, environmental impact, and they get degraded over time when they are processed like that. So you have to make up for that, for those losses. Okay, so then I'm going back to the first point. You have to synthesize it. You have an impact, etc. So it's not ideal. It's possible, but it's not ideal. So that is possible. Capture at point sources, and then we have some examples of things that can be done directly from the air.
Climeworks.
Just an example.
We're the Swiss company trying to help reverse climate change using direct air capture technology. How does direct air capture and storage work? In one sentence, you could say direct air capture catches CO2 and removes it from the air. The air is drawn into a collector with a fan, and CO2 is captured on the surface of a highly selective filter material that sits inside the collector. Next, once the filter material is full of CO2, the collector closes and is heated to around 100 degrees Celsius. Using the Carbfix method, the captured CO2 is then mixed with water and pumped deep underground where it mineralizes and can be stored permanently for thousands of years. You can join this exciting journey towards a climate-positive future.
Thank you very much. So that was just an example to show you that there are commercial companies already working on that and proposing technical solutions to actually do, I cannot switch to the next slide. Yeah, to actually do, thank you very much, to actually do the carbon capture directly from air. So you have seen it's not absorption, it's adsorption, so it's on the solid, right? But you also need, again, so once it is saturated, you also need some energy to release again the CO2, regenerate the solvent, and get the cycle right. Okay, what you can do with this pure CO2, so you have a CO2-free air, and then you have pure CO2 that you can generate here. What you can do is, as was shown in the video, inject it in deep underground, so it's storage, or you can use it in greenhouses to accelerate the growth of vegetables. Or one of the things you could do is to do CO2 capture and utilization, so to utilize the CO2, and that's what we are doing. We are mostly focused on. So I just mentioned two technologies to capture CO2. Just getting back to my tree, I added here a green sentence to show you that there are some calculations that show that for a given amount of CO2 that is captured, you would need 500 to 1,500 more surface of trees to capture the same amount of CO2. So trees are wonderful objects, but they are less efficient than the two things that I showed you just before, at least the direct air capture. So let's plant more trees, but don't get me wrong, we will not be saved by just planting more trees. We also need some technologies. Okay, I will switch now to CO2 capture and utilization. And so the idea is to say, okay, we can capture, we can regenerate and purify and get a pure CO2 stream. So what to do with that? And I was talking about utilization. We have to keep in mind that we all know that CO2 is a very stable molecule, right? You take methane that you get from the Russian fields in your house, or you take other organic molecules, you burn them, you will generate energy, you will be happy. But doing so, you oxidize your carbon to +4, and then this is the most stable molecule. You cannot go further, you cannot extract energy anymore from that. So what you should do, if you want to utilize it, is to try to go back on the ladder, right? And how to do that? You have to inject energy, okay? So there's no other way. You have to inject energy to the system to get back from the CO2 to something that can be useful. So one of the things you can do is to react it with hydrogen, because hydrogen, on the other hand, is a very energetic molecule, high energy. And so a long time ago already, Prof Sabatier was doing many studies on the trying to react CO2 and hydrogen. Okay, so putting them together, heating them, putting them under pressure, and for most of his work, nothing happened actually. So it was stable, nothing is happening until he put it in contact with what he called the finely divided nickel powder and realized that he could produce methane. So that is called the methanation reaction or the Sabatier reaction, and it's actually like a dream come true because you take CO2 and you produce methane. That's exactly what we want to do, right? I will come back to that. It's not that ideal. Okay? So you could imagine to capture the CO2 before emission, then to react it, to get the methane, and you get the fuel again. Okay, so it's perfect. One comment that I want to make, because I sometimes have the remark or the question, pay attention, methane is a greenhouse gas, a very strong greenhouse gas, 20 times more powerful than CO2. So of course, I wrote there, no leak, please. Because if you produce methane and you let it go, it's a nightmare, right? So CO2 gets hydrogenated to methane, but you keep the methane to be used and to be burned again and emit CO2 if needed, but certainly not to emit it in the atmosphere. Okay, a little bit of thermodynamics. If you look at those molecules, these are the molar fractions at the thermodynamic equilibrium. Methanation reaction, so if you go to the right, is an exothermic reaction, so it's favored at lower temperature. And so you can see that the position of the equilibrium at low temperature here is mostly methane and water, so that side of the equilibrium. So we have to work at relatively low temperature, right? If we go to high temperature, we will have an equilibrium that is less favorable with less methane, okay? But as I said, Sabatier, when he was reacting hydrogen and CO2, he didn't see anything for a while. Why? Because those two molecules, A and B, methane, CO2 and hydrogen, if they're just mixed together, nothing happens. Why? You all know that, you're a chemist, you have an energy of activation that is very high for that reaction. Energy of activation is high, so this exponential here is very low, so K is very low, so the rate of the reaction is very, very, very low, because this energy of activation is very high. So what we do as catalysis scientists is to try to find good catalysts that will have a good affinity for those two molecules. In this case, it's the ability to dissociate hydrogen, to dissociate or to activate CO2. And then they're put in a situation where it's easier for those two molecules to react with a much smaller energy of activation. Small energy of activation, large exponential, large K, large R. Okay? So if you don't have any catalyst, what you see is that the catalytic activity, so the rate of the reaction is zero. If you have a catalyst, so that's the way here, you start to see some activity and it increases, of course. Our job as catalysis scientists is to find the right catalyst, and the right catalyst in this case is a catalyst that will be active at low temperature, as low as possible, because we are dealing with an exothermic reaction. So what we do is to develop those catalysts. They are typically based on noble methods like rhodium, ruthenium, nickel. Nickel is not noble, but those kind of hydrogenating metals. And our job is also to disperse them, to have small nanoparticles, to have a large active phase. So a lot of surface sites for adsorption, dissociation, and reaction. So that's what we do in the lab, trying to combine CO2 and hydrogen to get methane by developing the right catalysts. So I will now enter into one part where I will discuss a little bit the results that we have in the lab. Then I will come back to more general questions. So one of the studies that we did was to study the role of the catalyst support, in this case it's titania, in these kind of formulations. We know that ruthenium is a very good catalyst, so Sabatier was studying nickel, but ruthenium is even better, right? But you have to disperse this ruthenium onto a support, in this case titania, and we wanted to study those interactions. So we started with a system that was kind of interesting. We thought it's a possibility to prepare a suspension of colloids, or nanoparticles of ruthenia nanoparticles, 2 nanometers, and then a series of different titania supports. You know that titania can be crystallized in different structures. So you have anatase, you have rutile, and you have a commercial support that is very famous in the field. It's called P25, and it's a mixture of anatase and rutile. So what we did is to prepare dispersed nanoparticles onto those titania. Thanks to this technique here, we could have a uniform distribution of all those ruthenia nanoparticles on top of those supports. And we targeted, of course, this exact same loading. So what we wanted to see is the role of the support itself. So you can see by electron microscopy very tiny ruthenium nanoparticles dispersed everywhere. So we were quite happy with this model system to start. Once you do this kind of impregnation, you still have to do a kind of calcination and then an in situ reduction, because what is active in the end is not ruthenia, but ruthenium, so the metallic ruthenium. And then we test them in the reaction. So this is what we found when we tested those three systems. As a reminder, what is active is the ruthenium, not the titanium, but yet when you deposit it on different phases, you get different catalytic results. So that was a bit intriguing, and we wanted to go further. So this one is not so good on rutile, anatase is okay, and P25 is much better, while P25 is just a mixture of those two normally, so it's a bit surprising. Right? So the question was why? We were not the only ones to observe this kind of strange behavior depending on the titania support, so just to mention some references. And we realized that actually it was this step that was responsible for those big differences. If you look at the catalyst after what we call the annealing, so the calcination if you want, you see that those catalysts do not look alike, right? Here you see big crystals. Here you see those kind of, sausages, or I don't know. And those smaller particles with patches, white patches, and small particles also on this one. So drastically different aspects, right? So we went, of course, a little bit deeper, and this is just part of a summary of what we found. So if you look at the XRD, so X-ray diffraction, the catalyst that was just prepared and just heated a little bit on anatase in this case, we see the pattern with the circles there, the typical patterns of the anatase titania support. We calculate a kind of parameter here, which is the split between those two most intense peaks there. And we found that anatase landed exactly where it is expected, so no big surprise. This is anatase, no problem. At low calcination temperature, we don't see ruthenium or ruthenia, but when we increase the calcination temperature, we start to see those diamonds here, rutile ruthenia. So this is the classical phase in which ruthenium dioxide will crystallize. So it landed exactly where it was expected, so no big surprise there. Okay, but the peaks there were not tiny, and they were a good indication of the fact that you have a big sintering, so agglomeration of the ruthenium oxide, formation of relatively big crystals. I remind you, big crystals, not so good for catalysis because you lose some active surface. So what's happening on the other supports? For rutile, in this case, we also have the expected peaks. Those triangles there belong to titania rutile, and they land on the expected position. Again, at low temperature, we don't see the ruthenia, but here at high temperature, we start to see a tiny little peak here. And what we notice is that it did not land on the expected position. It landed a little bit higher. So it landed a little bit higher, and this was also a bit intriguing to us. I don't have the time to go into all the characterizations, but as a summary, I can also say that the specific surface area of the catalyst decreased a lot when we did the annealing, the calcination. Also, when we analyzed the surface composition, so the accessibility of the ruthenium, we realized that the amount of ruthenium that was actually accessible to us, to our probes, by XPS or by hydrogen chemistry, was low, which was surprising. And also, when we tried to reduce the ruthenia, we realized that only part of the ruthenia was actually accessible for the reduction. So what happened? Actually, if you look at the fresh catalyst, so just after calcination, we have very nice rutile rods with tiny ruthenia nanoparticles, the black spots that you can see there. And after annealing, this is how it looks like. So it gets thicker, right? It's a bit strange. And then if you look a little bit closer, you see here the fringed or the lattice of the titania, and then you see a dark line here. And in bright field, you see a bright line here. What is that? In fact, this is the ruthenia, or UO2, that is growing as an epitaxial layer on the titania rutile. So in fact, it acts as a kind of glue between the different rods, and it gets stuck inside there and trapped and not available for catalysis anymore, right? So you could see that the rods kept the same length, but the thickness was increasing. In fact, you're just sticking all the rods together. So that's not good news for catalysis, of course, because that ruthenium that is there is not going to be active. We called it a kind of sandwiching of the ruthenium. It's not active for catalysis. What happens now with the P25, so that mixture that is better? Well, of course we have anatase, we have rutile, we can see them here, the blue triangles, the green dots, they are on the expected position, so we are happy. But as soon as we see, when we increase the temperature here, as soon as we see the diamonds here for ruthenia, we see that they're strongly shifted there, strongly shifted towards rutile. In this case, no drop of specific surface area. Reduction is okay, and also the dispersion, calculated by different techniques, is okay too. So we don't have this phenomenon of sandwiching, or trapping in this case. In fact, what we realize is that, I think I have to go there, is that we start with the situation where we have ruthenia everywhere, but after annealing, if you look carefully, we have some particles which have a dark edge, and some others which remain completely clean. Clean, dark, this one. So actually we could see that those with a dark edge were actually titania rutile. So the phase for which there is an epitaxy or an affinity with the ruthenia phase. And the others were anatase, because ruthenia does not like anatase, it likes rutile, okay? And there's a beautiful heart if you look at the image there. I like it a lot. I think you can see it even better. Beautiful, huh? Okay, so you saw the heart there. So the lesson from those experiments is that upon annealing, upon calcination, a lot of the ruthenium just go to the rutile TiO2 because there's affinity, there's epitaxial interactions, it's spread there, but the rods of rutile are kind of diluted into the anatase and they don't have the opportunity to get stuck together, right, and to form these sandwiching structures. So that is why we had these differences. And of course, knowing this, we wanted to check, to prove it experimentally. So we did an experiment where we took our two catalysts, so the rutile TiO2 plus ruthenia drying calcination, and then the other one with anatase, and in the end we mixed them together. So this is the performance of the rutile one, this is the performance of the anatase one. If we mix them together, for example 50-50, where should we land in terms of activity? Just in between, on the line, right? So that's what we did, and that's what we found. Now, if instead of doing that, you take the two supports, you put the ruthenium, you dry, and then you mix before annealing, right? You mix before the annealing. Then it should behave a bit like the P25 that I just showed you before, right? And this is indeed what we observe, either when you do the mixing at the very beginning or just before annealing, you have, for certain compositions, you have a beneficial effect of the mixing because you avoid this sandwiching, this sintering, and this trapping of the ruthenium. Time is passing very fast, so I will accelerate on this one. Another system, because I'm talking about e-fuels in general, so electricity, green electricity towards fuels, let's say, so I was talking about methane, but you can do it also with methanol. In fact, if you listen to the radio or look at TV, when we talk about e-fuels, we talk about methane, methanol, ammonia, and higher hydrocarbons that you can have via the Fischer process. So it's all related. So we have developed a technology to make catalysts that were quite active in the methanol synthesis. This is something we develop a lot in my lab. It's a bit special. It's called the aerosol-assisted soldier process to make heterogeneous catalysts. What we want to have in the end is a catalyst with an excellent control on the texture, so the porosity, the morphology, and something that could be easy to scale up and to bring to industry. So how it's working, we start with molecular precursors, so not solids, and we spray them, we atomize them as small droplets, which are dried very quickly. And in here, we also put some surfactants. Those surfactants, or soap molecules if you want, amphiphilic molecules, they will make micelles, right? And around those micelles, we will build the inorganic solid, right? To get, in the end, after calcination, we remove the surfactant, we have the pores that are calibrated with the right size for catalysts. So in fact, it's a concept that is a bit more than 20 years old and that allow you to make what we call mesoporous, for example, mesoporous or mesostructured silica microspheres. But with silica, you cannot do much in catalysis. So what we do now is to bring active elements like this molybdenum here, titanium here for different applications. And in this case, for copper and for the methanol, what we did, we start with silicon alkoxide that we hydrolyze or pre-hydrolyze, and then we mix it with a solution that contains the surfactant here. We spray it, and we hope to have this kind of structure. That's for silica, but if you want to do a catalyst, you have to bring in some active elements. So it's relatively easy. You just have to include here your copper nitrate, because you want copper in the end. And we were studying the effect of some dopants, gallium and zinc. Okay? So it's relatively easy. It's one pot. What you can do in the lab, just by spraying, drying, and collecting the support, you actually can do it at the lab, at the industrial scale, because with spray dryers of 30 meters high, producing tons an hour. These are the catalysts that we developed. So kind of nice spheres, porous. If you look at the elemental mapping, of course you get silicon, oxygen, the dopant, in this case zinc, and then you can see that the copper is very dispersed. This is something that we want in catalysis. We don't want big chunks of copper, we want dispersed copper. So that's quite nice. I told you in catalysis also we need pores. Molecules should come in, react, get out. Okay, so we need pores, and pores in this range, in the range of the mesopores. In this case, we target something like about 6 or 7 nanometers, which is the best thing we can have to have a high surface area, but pores that are large enough to have easy diffusion. Okay, in spray, in aerosol, we spray those small droplets and they are dried in 1 second or 2 seconds, so it's very fast. What we get at first is something that is completely amorphous. It's just silica with copper in it, right? But then when we calcine to remove the surfactant, to release the pores, what we see is the appearance of copper oxide, right? That's the calcination temperature that is done in situ in the XRD apparatus. And we see those peaks of copper oxide coming in, right? Coming out and getting bigger and bigger. From this peak, you can estimate the size of the copper oxide particles. And you can see that when you increase the calcination temperature, you increase the copper size. In catalysis, there's very often an optimum in terms of size. So that's a very precious plot for us. We can choose, okay, depending on the size you want, you can just choose the calcination temperature and you're happy. Okay. Cutting a long story short, also what we could evidence, and I will not spend time to explain everything that we found there, but what we could explain or demonstrate is that actually in the spray, we disperse the copper atomically in the silica first. Those gray circles here represent the micelles, so the surfactants. And then we have to calcine to remove the micelles and to have the porosity. But by doing so, the copper does not like to be in silica actually. And it tends to migrate and go to the surface and form a bit bigger particles, right? So that's what we saw in the previous plot. If you go too far, if you heat up too far, you will again aggregate or sinter those small particles and form bigger particles. So of course there's a kind of optimum that you have to find to form the porosity, to form the copper nanoparticles, but not too big, right? So that's what we did. And this process is called exsolution of the copper. So the copper is in the material, but then when you heat it up, it tends to go out, and you can control this to a certain extent. The good thing with this system is that we could show a doping effect that was already known, actually, the doping effect of gallium and zinc that we put in those formulations. It's already known, but in these systems that are made in one pot with everything all together, with the copper that is really inserted into the gallium-doped silica, for example, the effect of doping was huge. In fact, the yield with copper silica is very low. As soon as you put a little bit of gallium or zinc, it's a huge effect, a huge doping effect that you get. Okay, I will go back to more general thoughts for the end, and then I will finish with an example of an integrated process that we tried. General thought on CO2 sourcing and hydrogen sourcing, because, okay, nice. You in your lab, you take CO2, hydrogen, you make molecules, or okay. But this is a kind of metaphor that I like to do. Sometimes in the media we will see things like we're taking CO2 and we recycle it to methane. Oh, that seems great. But when we say that, we forget to say that to do that, we use hydrogen, right? Okay? So as a joke, I will change the slide and say, I have invented a new process that is taking sewage sludge and I'm recycling it to apple juice. I found something magic. Great. I can take this awful stuff and turn it into apple juice. But I don't say that in my recipe I have to put Petrus 20 ans d'âge, a 20-year-old age wine that is very, very, very expensive. And that's the trick to make the apple juice. Okay, it makes no sense, but you got my point, right? If you don't mention the Petrus, you're lying, right? Okay? So if you see, so you have to correct the title, yeah, right? You have to say that you have Petrus. So if you see CO2 recycling to e-fuels, I don't agree with that. You have to say it's the conversion of CO2 and hydrogen to methane and water, right? And the and hydrogen is very important because where is this hydrogen coming from? Okay? Designing good catalysts we can do. We do it. Other people do it. But the question now is which hydrogen are we going to use and which CO2? So, first, hydrogen. If today I want to build a plant to do this and I want to buy hydrogen, I will buy these bottles, and these bottles of hydrogen, 95% of the hydrogen that you can buy on the market comes from methane steam vapor reforming. Okay? Methane. Okay? So these are the reactions. Easy, you take methane, you react it with water, with a catalyst at high temperature, high pressure, you form CO2 and hydrogen, you separate them, and then you again react CO with water on another catalyst, etc., etc., and in total you have this reaction, and indeed you can produce hydrogen. Now look at this reaction, and look at this one. It's the same, just reverse. So if I use hydrogen to hydrogenate CO2, and this hydrogen comes from that reaction, I'm completely crazy, right? Because I have emitted as much CO2 as the CO2 I will capture there, right? And this is without saying that those reactions here, they are taking place at high temperature, high pressure, they don't have a full 100% yield, so it's complete nonsense, of course, right? So if you want to do this, why not? But you cannot use that one. This is called gray hydrogen. In fact, we have a kind of nomenclature. You hear it all the time in the news these days, so pay attention to that. There are different colors, but you can, if you want, you can remember only two. It's the gray hydrogen, that's the one I just mentioned. It's the cheapest, and it's the one that has emitted a lot of CO2 to be produced. Stoichiometrically, as much. So that's the gray hydrogen. You cannot use that one. If you use that techniques, but you capture the CO2 with one of the techniques I showed you before, it's called blue hydrogen. So it's still from fossil, but you capture the CO2, so it's already better. But the only hydrogen that makes sense in the end is the green hydrogen. It's the hydrogen that you will obtain from water electrolysis, and you feed your water electrolyzer with green electrons, right? So all I want to say is that my job as a catalyst designer and catalyst scientist, etc., it's nice to do, I'm having fun, but it's nonsense, and it's going to be useless if we don't make huge progress in producing massive amounts of green electricity that we can spend to do that, and that we will not use to, I don't know, load our cars or do whatever, okay? So it's a big challenge, huh? It's a big if, right? That's what I want to say. Technically speaking and economically speaking, the problem is on the electrolyzers. So it's still quite expensive to do the water electrolysis. And also, of course, installing a lot of wind turbines, etc., etc. Okay. So yeah, that's something that has to be said, I think, if we want to be honest. We hear very often, okay, green hydrogen produced via water electrolysis is much cheaper than gray hydrogen produced via methane reforming. I will put a question mark on that, and I'm going to be more optimistic than that. In fact, we see fossil resources with many spikes in terms of price, but with the general trend, upward trend, and green electricity with the general downward trends. And sometimes you see articles like this one, 2 years ago, 1.5 years ago, where the situation was so crazy on the markets that there were some spikes where it was more economically viable to produce hydrogen via green electrons than via methane. It was just for a few hours or days, I don't know. But it happened, and it's going to happen more and more often, and maybe curves will just cross. And in fact, politically, there is a momentum now where everybody is speaking about hydrogen, and I think it's still something that is going to be developed a lot. Why is it interesting? But of course, you know that when you rely on renewable energies, you have intermittency, right? So if you're just that day where there is not so much sun, not so much wind, you have a problem. You have to import electricity, right? So there's all these challenges of connecting the grids, etc., etc. So one of the things that we can think of is that when we produce a lot of electrons, green electrons, we cannot use them or store them. You could put them in batteries, but that's another story. Well, one of the things you could do is to feed an electrolyzer and to produce hydrogen. So that's the scenario that is called power to hydrogen. It makes sense. I mean, you have too much electricity at one point, you have the electrolyzer, you produce hydrogen, you have hydrogen. And hydrogen is very useful not only for energy sector, for the food sector, pharmaceutical. So we need hydrogen in many different places, right? But hydrogen is difficult to transport also. It's dangerous. It can, boom. So if you have CO2 at hand, you have another process, combustion process, steel industry just there, and you have CO2, you can capture it, blah, blah. Why not just turning it to methane or another molecule? But methane is quite nice because you can just inject it in the pipes and feed and heat the houses next door, right? So this is called the power to methane scenario. And if you don't target methane, but you target something else, but you still start from electrons, you have all this power to X, as we say, power to methanol, and it's also called e-fuel. So all the fuels, all the molecules that you can produce, and starting from those ones, we call them e-fuels. E-ammonia, e-methanol, e-kerosene, whatever. Okay? Just to show you the plans of Fluxys in Belgium, they are currently planning to build pipes to transport CO2, to transport hydrogen. Even though hydrogen it seems a bit tricky, but they are really planning to do that. So if you produce hydrogen at one place, but you have CO2 at another place, you have to transport all this. Practically speaking, one of the first methanation plant that was installed was 8 years ago now in Germany, in an OD plant, where they had the biogas available there. They had a big wind turbine also, and the surplus of electricity was used to make hydrogen, and then the hydrogen, CO2, methane to the village next door. So that was already operational 8 years ago, so it exists already. And there are big plants being built in different contexts. Why it's not working? Maybe it's the battery, I don't know. This is another project that is starting now. Okay. 2 minutes is fine.
2 minutes.
This is another big industrial project with Engie and John Cockerill and Carmeuse. Carmeuse is producing lime. Okay. John Cockerill is working on the electrolyzers. So they have, when you produce lime, you have to produce CO2. There's no way around it. You produce CO2, and then you can combine them via the methanation reaction that I just showed you, and then you can have methane and of course lime and so this is happening now. I had a last part that I'm not going to present because it would be more than 2 minutes. So just to summarize it, one of the things that we do, we have seen that we have to use renewable hydrogen. We could use this CO2, but there are some technical and economic limitations. So we are back to trying to use directly the CO2 that is in the effluents. This is a bit crazy because if you send this here to a catalyst, well, this is not only CO2, there's also unreacted oxygen. So you cannot send oxygen and hydrogen to a catalyst that is heated, right? Okay, there will be problems. There's also soot, sulfur oxide, nitrogen oxides. They will all kill your catalyst. So what we're doing is that we are trying to develop what we call dual function materials. A material that has two functions. One is to capture the CO2. So you have a first step one, where you will send the effluent to the dual function material, and CO2 is adsorbed on the material, and so you can release a CO2-free gas. And then when this one is saturated, we switch that valve and we send clean hydrogen. So the conditions are clean, okay? And on that dual function material, you don't have just the basic phase that captures CO2, you also have the famous ruthenium nanoparticles that can actually do the hydrogenation. There's a challenge there, of course, so you switch to hydrogen, and then you have step 2 and you have methanation, right? So there's, of course, many challenges that I can discuss afterwards if you have questions or if we have time. But basically, you can imagine a reactor that is working in capture mode, and then next to it, a reactor which is in regeneration, and then you switch from one to the other. So continuously, you can work on those efforts. I will not show you the results. That would be for questions, maybe, I guess. I just maybe conclude. I think we should work on CO2 hydrogenation. It's an important challenge, but we rely on green energy, green electrons, renewable electrons, and green hydrogen. That's really a take-home message that I want you to have. When we design catalysts, this is more for catalysis people. The role of the support is really important. We have seen some very drastic effects. We are inventing or developing aerosol modes to make innovative catalysts, and this can lead to big effects in terms of performance. And then I think it's pertinent, and we are seeing that now. We've been working on this combined process for 2-3 years, but we see many groups embarking into that now, many publications coming out. So this capture and utilization combined in the same process is something that I think is quite promising. With this, thank you very much for your attention.
Very interesting. All the original questions that it asked. That's what then to do, stimulate people grey matter, and then we've started to stimulate grey matter. So let's start asking questions. Do we have questions? Silence. Yes.
So on the silica particles that you had, you showed it in 2D with the pores in there, but surely they're tubular.
No, they're spherical because they come from the droplets.
So what is the driving force for the gases to go inside?
No, we put ourselves in conditions where molecules have enough time to diffuse in and out. So it's just so these are the things that we check when we do the testing, that we are not in diffusion limited range.
Right.
So if the gases pass too quickly around those spheres, of course they will not go in and diffuse. But we put ourselves in conditions where we don't have that problem. So molecules have the time to diffuse. It's simply diffusion. We don't push the molecules into the pores. It's just diffusion. We do now for these hydrogenation reactions. It's good to go to 3 bars, 5 bars, 8 bars, a little bit higher, but it's more related to thermodynamics, not to fluidics. It's just that the thermodynamics, if you put a little bit of pressure, you're shifting the equilibrium in the right direction because you do hydrogenation reactions. So on the right you have less molecules than on the left, but it's not related to diffusion.
But the other thing then is you're not controlling the stoichiometry of the thing, because the diffusivity of the carbon dioxide and the hydrogen must be very different.
That's a good point, but I guess that's not what is limiting in our system. It's the active side and what's happening on the active side. We have enough reagents. We put ourselves in conditions where we're sure that we have enough reagents diffusing fast enough. So interesting. Indeed, they do not diffuse at the same pace. Molecule water, it's like 2 angstrom or 3 angstrom in size, and the pores are 6 or 7 nanometers. So, I mean, it's large enough. That's what I mean.
Yes.
So, my questions are like because I'm a physicist rather than a chemist.
But it's going to be much more difficult to answer.
I'm really thinking about the extraction of the CO2, and I can certainly see your point that it's a lot easier to start with a high concentration from some exhaust pipe that is just part of another process. But long term, that only really makes sense if whatever is producing the CO2 really cannot possibly be done by any other method, because if it can, then we should be changing that first. So I'm asking myself, you showed us the big device that extracts CO2 from air.
Yeah.
Is anybody thinking about extracting it from water? Because the concentration of CO2 in the sea is at least 20 times higher than it is in the atmosphere. And I'm just wondering if anybody is thinking about this.
Not me. I don't know. That's a good question. But I don't know. Probably on the engineering side, it's going to be more difficult, maybe, because you have to process water in terms of fluidics and pumping and all these things. It's going to be a bit more difficult. What we do is actually, behind you is someone is sitting working on that, is to absorb CO2 in water and then convert it, capture by absorption in water. But the reverse, I'm not sure how. I haven't seen any example. Reason? I don't know. Probably things related to fluidics, engineering. Now, coming back to also the other point where you said there are no there's no way around that process that produces CO2. The example is cement. I mean, if you want to build houses, you need. You take CO3 and you want CaO. So you emit CO2. You don't have any other choice. So it's not only about burning fossil fuels, it's also this. And there's no way around it. So for those things, I think it makes sense to work on capture.
For a second, there are some flow from looking at the process of the planet's area and that sort of thing. There are kept routes to cement that use carbon dioxide.
Yes.
They're looking at ways of actually using it as a capture way. And one thing I was thinking about as well is the concept of it's all this green hydrogen. I mean, I know that there's a plan for all ammonia in Europe to be made by renewable, electrically driven green hydrogen. And God knows where that's going to come from. And if they use all that, there's none left for anybody else, really.
The ammonia, there were plans with Jordania, or in the desert. They produce all the electricity with the sun.
Yeah.
And then hydrogen, and then they don't transport hydrogen, but they reduce nitrogen to get ammonia, and then they transport ammonia in Belgium.
Yeah.
So that is one of the current plans on the ammonia.
It's going to have to be a very, very, very large scale to replace ammonia production completely, which is the plan. At least it's written there. All these things are written there. Whether they actually occur.
Well, yes. I just wonder how much double speak is going on here. Because you're talking about making something that's going to take something away, and then it's going to put it back, and then it's going to use it as I just the net CO2.
You delay.
You're sort of on a process where there seem to be so many cycles going on. You wonder just whether at the end of the game you're actually ending up doing anything that's worthwhile.
Yeah, that's true.
I'm sorry, this may sound like a very, very stupid question once again, but it seems to me that we're turning around in circles and not really getting to the, do we want to get rid of CO2? Well, if we want to get rid of CO2, then we need to put it somewhere where it doesn't do any harm.
So
because we're just using CO2 to make methane, which is then going to burn to make more CO2. Well, this is even the Mad Hatter couldn't come up with a better scheme for lunacy than that.
But I remember I used to work for British Gas Research many years ago, 80s, 90s, and at that time the edict was methane was too valuable to burn. Mm-hmm. Really, nothing's changed much, but we still burn a lot of it. And we spend a lot of time working with high nickel co-precipitated catalysts for methanation. But that was more carbon monoxide, hydrogen, but also there was a reasonable amount of carbon dioxide in that mix that we were simulating for big plants. I mean, 50 bar, 600 degree stuff. And it's interesting that we're still. I mean, we were doing sort of titanium stuff as well, just to see if we could do that, but we stuck
more
with co-precipitated stuff just because it was resilient to the sort of treatment we do to general plants. But then we found all the little C and we stopped doing it because that was going to use coal to make so much.
In my title there was also e-fuels, because sometimes people think about e-fuels to feed our cars.
Yeah.
You know, so to replace kerosene or benzene. I'm not sure that's going to be a good option because you have all the energy that you have to spend to capture the CO2, all the energy to produce the hydrogen, all the energy to do the not the methanation, the hydrogenation, and then the Fischer-Tropsch process to get to the higher organics that look like the petroleum that you put in your car. And then what you have to keep in mind also is that the energy that you put in your car, the yield is like about 30% or something like that. It's very low, right? So there was a calculation that was made by I don't know who kind of institute. They were saying that for a given amount of energy that you get from the sun, if you use that sun to make electrons and to load your car, your electric car, directly, you can use 70% of that energy. So it's kind of, if you take those electrons to make hydrogen, to hydrogenate CO2, to get to those fuels, and then you take those fuels and you put them in an engine, in a car with a regular thermal engine, you get 12 to 16% of what you got from the sun. So it's I think for those kind of applications, it's nonsense.
The shipping industry doesn't.
But yeah, there are some niche, yes, aviation, because aviation you're not going to electrify aviation, except solar impulse.
It is much more
narrow.
Yeah. And then there's the point about we were talking about using point sources, carbon capture.
Yeah.
Then you have the issue of how do you produce the green hydrogen next to the point.
Next to the point source.
So, but
we're not there yet. So technologically speaking, we have some solutions, but then if you look at the whole picture, it remains kind of complicated. And that goes back maybe to one of my first slides that we have. So we should have to think of using less, emitting less.
but we also need your work because we also need to know what catalysts work and what is the most efficient way of doing this.
Other questions? What about the availability of these is that a problem?
Yes, it's a big problem, and still today, when I submit a project and I have to defend it, and I say I want to use ruthenium, sometimes I get, no, you won't get the project because you use ruthenium. So that is something we have to be aware of, but it's the same with batteries, with the cars, with all the elements that you have in the wind turbines, in the solar panels, etc. So it's a huge problem, I'm sure. Now, what we have to realize in catalysis is that a catalyst is by definition something that accelerates a reaction, and in the process is not affected.
Yes.
So that's the theoretical definition, right? Of course, the catalyst gets old, gets deactivated. You have to discard it, but usually we don't discard them. We have recycling things, and we recover everything. So I think it's something we have to think about. Whenever possible, we have to switch to more abundant elements, of course. If we find the dream catalyst with one of those rare elements, it's not. I think it can still make sense if we have the whole process well mastered. We have high performance. We can recycle. We can have a stable catalyst. We can reuse it all the time. It's not like fuel that you use. It's something that stays in your plant and that you reuse or you recycle or you regenerate. So it's something we have to be aware of, and we have to mitigate that risk. But I would not say it's ruthenium, don't do it. I don't agree with that.
So where does it come from, the ruthenium? Which countries?
Mines, ruthenium, I would say Africa and all these things, like with the cobalt mines and things like that. I'm not sure. Ruthenium, I'm not sure. I said.
Well, a lot of the actinides and lanthanides that are used in catalytic converters and wind turbines.
Yeah.
A large part of the market has been cornered by the Chinese.
Who are these rare earth minerals?
Yeah.
Ruthenium is a rare earth mineral? Maybe, I don't know, yeah. Because if that's true, that's a problem, right?
Well, there's a major problem there, because I mean their strategy has been very simple. It was to dump cheap stuff on the market, eliminate the competition in other countries, and then put an embargo and put up the prices. That's essentially what they've done in the area of most of the elements that are used for wind turbines and things like that.
There's a professor in Liège, I forgot his name, who was on the podcast. Maybe you know my colleague Francesco Contino from the UCLouvain. He's an expert in energy, and he's having a podcast. It's in French, but on energy. And they were mentioning this, and they were saying also that it's not true that we don't have important elements in our grounds. We do have some, not everything, etc. But we decided willingly some decades ago not to do mining anymore in our countries, and to leave it to, for example, the Chinese, etc., because it's a work that nobody wanted to do anymore here. And so now there are thoughts of saying, okay, but here, this element, that element, we still have it in our grounds. We should go back and still have some mining activity here.
There's plenty of opportunity to ask more questions during the drinks and nibbles that are going to follow. Let's join with the...
Thank you again.
Thank you once again. And